Hi, today's lesson we are going to talk about inertia. In particular, the inertia of an aluminium profile. So, let's go back to school days quickly and remind ourselves we learned at school about the concept of inertia. When we learned about inertia at school, we were speaking about the resistance of an object to stop moving once it's already moving, or the resistance of an object to start moving. When we're talking about aluminium profiles, when we refer to the inertia of a profile, we are talking about that profile's resistance to bending or deflecting. And therefore it becomes important in terms of what we learned in our wind load 1 lesson, which is about minimizing the deflection of the aluminium profiles. So let's try and grasp what we mean by this concept of inertia. To demonstrate it, I'm going to give 1 or 2 simple examples. If I was to take a solid bar of aluminium, not a hollow profile, but a solid piece of aluminium, let's say that piece of aluminium is 10 millimeters in that dimension, and 20 millimeters in this dimension, and I gave you a short piece, let's say a 50 millimeter length of that piece of aluminium. I think you will all agree that if I was to take that piece of aluminium in my hand and try and bend it, I probably wouldn't be able to bend it at all. Okay, now I take that exact same bar of aluminium, 10 millimeters by 20 millimeters, 20, not 200. And this time, instead of giving you a short piece, I will give you a 2 meter length of that solid aluminium bar. Okay. Now I think we'll all agree that I would be able to relatively easily bend that aluminium bar. Now, although the IX value itself, or the inertia value of this particular profile does not change, the function of the length of that profile dramatically affects the flexibility of that item. And I think we've all seen it in the aluminium industry. If I was to take a short piece of any aluminium profile and try and bend that profile would feel extremely rigid. Yet if I picked up a full 6 meter length of this profile, the profile would feel very floppy. And we will talk about the maths, maybe not in this lesson, maybe only in the future lesson, which explains why the profile becomes so much more flexible as the length increases. Alright. So to understand this concept of inertia, I want to look at 1 or 2 other examples. Remember that the inertia of a profile is defined by the shape of that profile. In fact, if you take any CAD drawing of an aluminium profile, through that CAD package you can calculate the actual inertia value. Okay, let's take another simple example. If I was to take a piece of flat bar, alright, and I took that long, let's say 2 or 3 meter length of flat bar, and I was to simply only hold it on this one side, I think we'll all agree quite quickly that that end would tend to sag, just due to the effects of gravity. You can imagine I'm holding a long flat piece of metal. Naturally that piece of metal will sag on the far side. But now I take that exact same aluminium profile, my piece of flat bar, and I hold it in this orientation. Not very nice drawing. Okay, what happens now? If I hold that bar, just holding the end of it, alright, that bar will no longer sag at the end. But what will tend to happen is that bar will start becoming flexible in the horizontal direction. So it will start moving left and right as opposed to up and down. And the reason why I'm demonstrating you that is to show you that the inertia value of a profile is a function of which way that particular profile is orientated as well. And in fact, when we're talking about the inertia of an aluminium section, we not only talk about an Ix value or the inertia in the X direction, we also talk about the inertia Iy in the Y direction. Now the units of inertia are centimeters to the power of 4, and we will see at a later stage where that's to the power of 4 comes from. But for now, we're just trying to get some understanding of what we mean by the inertia of an aluminium profile. So, going back to our basics from Wind Load 1 course, I said the national building regulations, if I was to draw a section through a window, and let's say here I'm looking at a mullion, that mullion is only supported at 2 points. And the national building regulations limits the maximum amount that this aluminium profile may deflect from its normal position. And the force which is causing the deflection of this profile is that parcel of wind which is impacting against my window. As mentioned in the wind load lecture, this maximum deflection is the length of the profile divided by 175. So what this is really telling us is it's defining how stiff that particular profile needs to be. The stiffer the profile is, the higher the Ix or the Iy value in centimeters to the fourth, the more that that profile is going to resist the deflection due to that wind load. Now, the problem is, I can't build myself a window like this. Let's say that window's only got a single mullion in it. Okay, I know that that window is supported all the way around on the outside, where it's attached correctly to the brickwork or lintel or I-beam, whatever is around that window. And the profile that I'm concerned about is this profile here, because it is only supported at those 2 points. Now, I can't build that window, install it in place, and then sit with a ruler and say, well, I know the length of this mullion is, let's say, 1750, which means that 1750 divided by my 175 equals 10 millimeters. I can't sit and wait for the wind to blow against this window and measure that that mullion is not moving by more than 10 millimeters. So I actually need to convert this value here into a minimum Ix value. A minimum stiffness that that profile must have in the X direction, and we always consider the X direction between the outside of the window and the inside of the window. That is our X direction. I need to convert this length over 175 into an equivalent minimum Ix value. Then what I can do is I can say my profile needs a minimum stiffness of whatever that Ix value is, and then I ensure that when the wind, according to my wind load specification, blows against this window, that mullion will not deflect or bend by more than its length divided by 175. So let's have a look at what affects a profile's Ix and Iy value. And to do that, I'm going to go back to my simple aluminium bar. If I've got an aluminium bar, all right, how do I determine, or how do I define what the Ix and Iy values of that aluminium bar is? Well, simply, I start off with what is called the centroid, which is effectively the center of gravity of that profile, moved to the edge of that profile. And through that centroid, I put an X and a y-axis. Now, I know that when I'm holding this profile up vertical like that, it becomes rigid in the vertical direction, but it becomes floppy in the horizontal direction. And if I was to take that profile and hold it flat, I know that it would be rigid in the horizontal direction, but floppy in the vertical direction. So really what determines this Ix and Iy value is actually the amount of metal on that design or that profile and how far that metal sits from that particular axis. So the more metal I move away from this axis here, the stronger that profile becomes in that direction. In this case would be the y value. So my Iy value would be increasing. If I look in my x direction, all my material is extremely close to my vertical axis. So I do not have much strength in the horizontal direction. And therefore when I'm holding that profile up like this, it's rigid vertically, but it is floppy in the horizontal direction. Now, in this situation, I would expect my Iy value to be much greater than my Ix value. And typically I might have a situation that on a profile like this, the Ix value is, let's say, 1 centimeter to the fourth, and the Iy value might be 12 centimeters to the fourth. Okay, now if I take that exact same profile and I hold it in a horizontal direction, okay, I once again work with the centroid. I put a vertical and a horizontal axis through that centroid. That is my x-axis, that is my y-axis. Now what has happened is the amount of material and the distance that material is away from the axis in the vertical direction is low. So this profile is weak in the vertical direction, which means if I hold it out like that, it's going to droop. Whereas now in my horizontal direction, my material is nice and far from the axis, so it has greater strength in that horizontal direction. So in this situation, what actually happens is that my Ix and my Iy values swap around. So one cannot just simply say, what is the Ix value of a particular profile? If I take an aluminium profile, like this, and I say to you, what is the Ix value of that profile? Well, it depends whether the profile is orientated like that, or if the profile is orientated like that. So, as a convention in StarFront, what we do is we keep everything, or all the profiles are orientated in such a way that the Ix value is the critical value that we need to work with. And if you go into StarFront and you go into the edit menu, go to the section file, you call up any of the aluminium sections on that file, you will see the Ix and Iy value of every section will be listed for you. So let's understand, for example, how this affects the selection of mullions. I'm building a window. That window looks like this. It's a fixed window with a single mullion. I know that my window is 1200 millimeters wide. My window is 1500 millimeters high. And I decide that this window must be designed at a wind load of 1500 pascals. What I can do is I can do the calculation and I can determine that the required Ix, or the minimum Ix value for this aluminium profile, let's say is 12.8 centimeters to the fourth power. Okay. It is based on the fact that I can take the length of the mullion. Let's say the length of this mullion is about 1460. I can take 1460 divided by 175, which gives me 8.32 millimeters. So in other words, if I was to build this window, a 1200 by 1500 window, with a single mullion, I need to ensure that that mullion does not deflect by more than 8.32 millimeters. Once again, that is not a practical entity or quantity to measure, so I need to translate that into an equivalent IX value. Once I know what the minimum IX value or the minimum stiffness that that profile needs to have, then I can have a look at my options of those profiles and I can decide which is the correct mullion to use. So let's assume that we are making this using the Swift 28 system. Alright, if I look on a simplistic level, this is what a mullion looks like. Okay, I would have a piece of glass sitting here, and I'd have a piece of glass sitting there. Alright, this would represent the inside of the window, this would represent the outside of the window. Now, if I take, on the Swift 28 system, a standard 28 millimeter mullion, the IX value is approximately equal to 2.5. I think it's 2.3, something like that, but it doesn't matter. Okay. That will be the stiffness of the profile in this direction. Because as I said, we always consider the inward-outward direction to be our IX value. If I then looked at, say, a 54 millimeter mullion, so that is your standard Swift 28 mullion. If I look at a 54 millimeter mullion, draw a bit more accurately, this part stays identical as the standard mullion. But what happens is that mullion now grows towards the inside. I would still have my glass sitting there, my glass sitting here. But what has happened on this profile is the profile, I have moved more material further away from my vertical axis. So this material here and this material here, that's my centroid of my profile. Effectively, that material is moved further away from the axis. And that's what increases the strength of that profile. So I might find that the IX value for a 54 millimeter mullion is, let's say, approximately equal to 8.6 centimeters to the fourth. So it's also centimeters to the fourth. Okay. And then if I take a 70 mm mullion, what happens on a 70 mm mullion is that this profile grows towards the inside even more. And in fact, what we do is we increase this wall thickness. So now we have a situation that we've moved even more material away from that centroid. So there I would once again have my X and my Y axis. And now on a 70 mm mullion, I've moved even more material away from that axis. So my IX value might be something like 25 centimeters to the fourth power. These IX values are purely a function of the shape of that particular profile. When I do my calculation, I determine that according to my specified wind load, I need to limit the maximum deflection, the maximum amount that this profile may move. The limit is the length of that profile divided by 175. So in this example, that gives us 8.32 millimeters. And then I convert that into an equivalent IX value or a minimum IX value, telling me that the stiffness of this profile needs to be at least 12.8 in order for this window to not deflect beyond the legal limit. Then what StarFront does is it's quite simple. You design that window, by default it will automatically put a standard mullion in. So this was our standard mullion, this was our 54 millimeter mullion, this was our 70 millimeter mullion. And then it says, okay, it does a calculation, says I require an IX value of 12.8. And then it says, alright, well, a standard mullion's IX value is only 2.5, so we can't use that option. It then goes to the next mullion up, which is the 54 millimeter mullion, and it says, all right, that mullion has got an IX value of 8.6. It's still not high enough, so I can't use that. And then it says, all right, well, what if we use a 17 mm mullion? That 17 mm mullion has an IX value of 25, which is strong enough, so StarFront will automatically put that mullion in for you. Now that process happens automatically. In the second level of wind load in lecture, we will describe how these calculations are actually calculated. But for now, you just need to accept the fact that StarFront will translate the distance, the maximum deflection in millimeters, it will translate it into a minimum IX value for you. And in most situations, the program will automatically put the correct mullion in for you. What would happen now if I became ridiculous and I said, well, I want to make this window 2.5 meters high? What that will do is it will force this IX value to be much greater. So on 2.5 meters, I might have an IX value, a minimum IX value of, let's say, 45 centimeters to the fourth power. Okay, now the program will go through the same process. Standard mullion is 2.5, it's not strong enough. 54 mm mullion is 8.6, that's not strong enough. 70 mm mullion is 25, that is also not strong enough. And that is when you get a big red box on your screen which says there is no mullion strong enough to meet the specified wind load. Other stiffening is required, or other strengthening is required. Now what we mean by other strengthening we'll cover in another lesson, but when you get to the situation as a beginner in StarFront, when you get in this big red warning coming up and saying there is no mullion strong enough, then you need to say to yourself, well, I am most probably utilizing the wrong system. I am utilizing a casement window system where I should be maybe using a shop front system. So it's an indication to you that you are exceeding the limitations of how that system was designed and what the capabilities of that particular system are. Alright, so I hope that will give you a little bit more of a feel for what inertia is. We are going to talk about how this calculation is done, from taking a minimum or a maximum deflection and converting that into a minimum IX value. But for this lesson, this is all that you need to understand. And please realize that it is part of the National Building Regulations to ensure that you are specifying the correct profile. And that profile does not only apply to mullions. Remember, the exact same calculation applies for transoms, it applies for interlocks, meeting styles, where two door styles come together on a double door or on a Vistafold door. So this calculation needs to be done several times. And as long as you are not getting the big red warning on StarFront, which says you have exceeded the maximum allowable value, then you can be confident in knowing that StarFront will automatically put the correct profiles in for you and ensure that your design complies with the regulations. Once again, guys, thank you. I value your time in taking the time to follow this course and to learn a little bit more about the StarFront program. I hope that we are going to see each other again tomorrow for tomorrow's lesson. Thank you, stay safe, stay happy. Bye-bye.